Bismillahirrahmanirrahim. Dear students, welcome to the Electrical Engineering channel. In this lecture, we will discuss the input and output curve of a power system. And this is the new topic in the course of power system operation and control. And this topic is related to power system economics. And in this topic, we will be discussing how the power system can be made more efficient and how the power can be evaluated from the generator at minimum cost, right? So we have two types of curves, input output curve. And if we have input at the y-axis and output at the x-axis, then that curve will give us the incremental fuel cost. And if we have the output at the y-axis and input at the x-axis, then this curve will give us the fuel efficiency. Okay, so in this graph, uh, the slope is equal to the input divided by the output, and input in this case is either the energy or power, and it is given in British thermal unit or British thermal unit per hours, and this actually corresponds to the quantity of fuel, right? And here we have the output. And if we are saying that we want to increase the output of our generator from, let's say, 50 megawatt to 60 megawatt, then the amount of the fuel we have to inject will rise by, for example, 1000 BTUs, right? So that curve will give us the fuel cost. If we want to increase our output, then the input or the fuel will also increase. So that will give us the fuel cost. And if we are increasing the input, right? If we are increasing the input of the system, then the output will increase. So this graph will give us the fuel efficiency. If we are injecting more fuel into the system and we are analyzing how much output has been increased by the generator. So this curve will give us the efficiency. So this is the difference between these two types of curves. So the first curve will give us the incremental fuel cost, which is the slope, and the second curve will give us the fuel efficiency, and m1 is equal to minus 1 over m2. So this is the relationship between these two curves. So I will define the British thermal unit, and BTU is a traditional unit of heat defined as the amount of heat required to raise 1 pound of water temperature by 1 degree Fahrenheit. So this is the definition of British thermal unit. And since we are discussing power system economics, so we will be dealing with the first curve. So this curve is actually related to the incremental fuel cost. So we will be dealing with this curve. So before proceeding to the example, I will show you the derivation, which is very important. And this is the derivation based on the distribution of load between the units. And here we will denote the input by Fi, the output will be denoted by Pgi, and I is the unit, right? So we have, if we have three units, then I will be equal to 1, 2, and 3. Similarly, the input to the unit, which is I, will also be 1, 2, and 3. So F1, F2, and F3 will be the three functions. And the unit of this fuel cost function is dollars per hour, right? So this is called fuel cost function, and this is called output power. The fuel cost function actually describes the variation of the fuel or variation of the consumption of the fuel with respect to the output power of the generator. So if we are getting more power from the generator, definitely the fuel consumption will also be high. So the cost in dollars per hour will also be high. So that trend can be represented by a first order polynomial, or by a second order polynomial, or by a third order polynomial. So this fuel cost function is actually the characteristic of the generator, and it denotes us how the generator behaves when its output is increased. right? So how the generator will charge or will cost or will consume the fuel if the output connected to the generator is increased. So in this section, we will be discussing mostly the second order polynomial, right? So this is the general second order polynomial and it is represented by AI divided by 2 PGI square plus BI PGI plus EI. So why we have used AI by 2 over here? Because in the next step we will see that are evaluating the derivative of this fuel cost function. So if we have divided by 2 term over here and if we evaluate its derivative, then it will become PGI, right? AI PGI plus BI. So here in that case we won't have any 2 over here. So that's why we already have placed a 1 by 2 term uh, over here, so that after taking the derivative we get the simplified expression. So this is our fuel cost function and it is given in dollars per hour, and if we evaluate the derivative of this term, then we will get incremental fuel cost, which is the derivative of this term with respect to PGI, and it is equal to AI PGI plus BI in dollars per megawatt hours, because we have evaluated the derivative with respect to the power. So we will have megawatt in the denominator term. If we have a plant with 2 units, then we have to assume lambda as the same for the economic load distribution. If this lambda is evaluated as same for both the units, then our system will be most economic. And I will show you with the help of an example that uh, equal values of lambda for both the units will result economic results. So lambda is equal to dfi over dpgi, and for the first generator it is equal to a1 pg1 plus b1. For the second generator, incremental fuel cost will be equal to a2 pg2 plus b2, and for the economic operation both lambdas will be equal to each other. So lambda 1 is equal to this is lambda 2, and both are equal. Lambda 1 equal to lambda 2 equal to lambda. So we can get pg1 from this equation, and pg1 is equal to lambda minus v1 over a1. We can evaluate pg2 from this equation, and it will be equal to lambda minus b2 divided by a2, and pg1 plus pg2 will be equal to this plus this, and we can separate all these terms, so it will be lambda over a1 minus b1 over a1 plus so on. So pg1 plus pg2 will be equal to 1 over a1 plus 1 over a2 times lambda minus b1 over a1 plus b2 over a2. So we have two terms now, and this lambda term can be kept over here, and this term can be taken to the left hand side. So we will have 1 over a1 plus 1 over a2 lambda is equal to pg1 plus pg2 plus b1 over a1 plus b2 over a2. So lambda will be equal to 1 over a1 plus 1 over a2 inverse into pg1 plus pg2 plus 1 over a1 plus 1 over a2 inverse into b1 over a1 plus b2 over a2. So these are simple algebraic steps, and this can be written in general with the use of a summation, and summation I is equal to 1 to 2 1 over ai inverse pg1 plus pg2 plus again the summation, and this can also be written in the summation form. So again we have got an analogous expression for lambda which we had for each individual unit. So here we had lambda equal to a1 pg1 plus b1. So now we have lambda equal to at pgt plus bt, right? So this is lambda which is equal to at pgt plus bt, where at is equal to this term and bt is equal to this whole term, which is at times this summation. So this is very important formulation which we will use extensively while solving the fuel cost problems. Now let's consider the first example in which we have 2 units and the incremental fuel cost functions are also defined for them. So this is A1, this is B1, this is A2, and this is B2. Both units are operating at all times and total load varies from 250 to 1250 megawatts. Maximum and minimum loads on each unit are 625 and 100 megawatts. So these are the maximum loads which can be applied on each unit, and this is the minimum load which can be applied to each unit. So each unit is operating at 100 megawatt minimum, and maximum load which can be applied to one unit is 625 megawatts. So now we have to evaluate the incremental fuel cost functions for different loadings, right? So when we have a total load of 250 megawatts, then this is our lambda 1, this is our lambda 2 at the lower limit of 100 megawatts. So therefore, as load increases, additional load should come from the unit 2. So here we can see that the incremental fuel cost of the second generator is smaller as compared to the first generator. So any additional load in excess of 100 megawatt will be applied to the second generator. So at 250 megawatts of total load, 100 megawatt will be given to the first unit because 100 megawatt is the minimum unit that each unit must have, and the other 150 megawatt will be assigned to the second generator, and lambda 2 will be equal to $7.84 per megawatt hour at 150 megawatt. So this lambda 2 can be evaluated very easily from here. So if we have 150 as PG2, then lambda 2 can be evaluated. And unit will supply additional load until lambda 2 is equal to $8.8 per megawatt hour. So unless this lambda 2 becomes equal to 8.8 megawatt hours, which is the incremental fuel cost of the first generator, then additional load will be applied to the second generator. When lambda becomes greater than lambda 2 becomes greater than this lambda 1, then the load assignment will be calculated by that expression. So at lambda 2 equal to 8.8, Eg2 is evaluated to be 250 megawatt. So when we have a total load of 350 megawatt, we will use 100 megawatt as the load of the first unit and 250 megawatt as the load of the second unit. And when our load starts increasing from 350 megawatt, then we will use these formulations to evaluate the load sharing. So first we will calculate AT, which is calculated using this expression. BT is evaluated using this expression. And for each unit, EGT is equal to, let's suppose, 500 megawatt. So for this amount of total load, we will evaluate lambda, which is equal to $9.4545 per megawatt hours. And PG1 is equal to this value, 181.8182, and PG2 is equal to this value. This is our lambda B1, A1, and here we will use B2 and A2. So these are the two values of PG1 and PG2, and if we add these two values, we will get this 500 megawatt. So this is how load sharing can be calculated, and for each amount of total load, this load sharing is shown in this table. And for a total load of 250, 100 will be assigned to the first generator and 150 will be assigned to the second generator. And this is our incremental fuel cost, which will be the smaller value of the two generators. And here it is 8.80 for 350 megawatt. For 500 load, we have this incremental fuel cost, and this is the load sharing at 700 megawatt. These are the values, and so on. Up to 1250 megawatt, we have 625 and 625 because this is a constraint which has been defined in the problem statement. So 625 is the maximum load which must be applied on each unit. We cannot apply more than 625 megawatt at any generator. And at 1175 load, this is lambda, this is 550 megawatt on the generator 1 and this is generator 2. Since the incremental fuel cost of the first generator is high, so you can see for all these values, the load applied to the first generator is slightly smaller than that applied to the second generator. So we can plot this PGT with respect to lambda, and this plot is shown in the textbook over here. So this is our PGT and this is our incremental fuel cost. So as PGT increases, lambda also increases, which you can see over here. Lambda is also increasing, and we can also plot PGT with respect to PG1 and PG2, and this is the plot. Here we have PGT, and this is the PG1, which is load of the first unit, and this is the load of the second unit, which is slightly higher than the load on the first unit. And at the loading of 1250 megawatt, both PG1 and PG2 are equal to 625. Now, if we are asked to apply equal loads on both the generators, then we have to evaluate how much more expense we have to add to the system. So determine the saving in fuel cost in dollars per hour for the economic distribution of a total load of 900 megawatt compared with equal distribution. So if we apply equal distribution and if we apply the economic distribution, then what will be the difference, right? So let's evaluate this. So we have to integrate lambda with respect to PG, and this integration will give us the fuel cost function. So we have to integrate incremental fuel cost function and then we will get fuel cost function. For the first generator, this is our lambda, and initially we had applied 400 megawatt to the first unit when we had total loading of 900 megawatt. So this is 900, this is PG1 and this is PG2. So now we are asked to apply equal loads on both the units. So it will be 450, this will also be 450. So we have to integrate this first lambda from 400 to 450. So this is very simple integration, and after putting these limits, we will get the answer of $570 per hour, which is the fuel cost function of the generator one. So $570 per hour more uh, fuel or more cost will be added to the first generator. For unit 2, before we were applying 500 megawatt load. Now we have to apply 450 megawatt load to the second unit as well because we have equal sharing now. So let's integrate this function, and after this integration and putting the limits, we get minus $548 per hour. So this fuel cost has been reduced by $548 per hour. Now negative sign indicates a decrease in the cost. So total saving is equal to 570 minus 548, which is equal to $22 per hour, and it is equal to $192,720 per year. So this is the amount which we can save if we are applying the economic operation instead of the equal sharing on the two generators. So I hope that lecture was quite interesting and understandable, and I hope you have understood the concepts which are discussed in this lecture, because we have also solved a simple example based on the formulations that have been developed. For watching more lectures, please subscribe this channel. Until the next lecture, it's goodbye.